All right. Today we are having a review. That's correct, right? So you guys don't care about transistors yet. So let's remove all this crap. What would you care to talk about?
What is your bonus question?
The bonus question is going to be a filter circuit.
Would it be worth going over that just really fast?
Sure, I can absolutely go over a filter question really fast. So I'm just going to make one up right now that might be similar to what I would expect of you. Okay. So let's say that we had the following circuit or filter. Go away. I might give you a simple circuit like this and ask you to tell me what the frequency response is, or the transfer function, I guess would be a better way to put it. So H of omega would be equal to what? Well, obviously then you would need to work this guy in the frequency domain. So using simple rules for voltage division, H of omega should be the voltage drop over the inductor in parallel with the capacitor. So that would be J omega L times 1 over J omega C divided by J omega L plus 1 over J omega C. All of that divided by R plus that same thing, J omega L times 1 over J omega C over J omega L plus 1 over J omega C. Because this is a bonus question and I'm not giving you, I don't want you to dedicate 20 minutes to reducing fractions and this, that, and the other. That is literally a perfectly acceptable final answer for this guy. So if you find yourself with an abundance of time, you could multiply the numerator by J omega C over J omega C and clear some fractions, and the same thing for the denominator, but that is not remotely expected of you for the exam. So it would be a simple question like this where I give you some odd looking little filter circuit with some combination of resistors, capacitors, and inductors, and then you apply voltage division and tell me effectively what the ratio of the resistances is that will give you the transfer function H of omega, where, just to be super clear, this is determined by taking the phasor output voltage as a function of omega and dividing it by the phasor input voltage, where we assume that Vn of omega is just 1 angle 0 to make our line. Technically speaking, I guess I might have skipped a step here, in as much as what I have written is just the ratio of the impedances in the voltage division equation, because I know I'm going to wind up dividing both sides by Vn. So I did skip that step, but that's really all it takes. That is the level of competency I expect of you for the in-class portion of the exam. For the take-home portion of the exam, there will be a filter circuit wherein I will ask you to specify the size of components to achieve a certain center frequency and certain bandwidth for either a band pass or band stop filter, which we went over all those equations and all that kind of good stuff. And if you don't have them, they're on YouTube at this point. So that's what I expect you to know for filters. Any other questions regarding filters or anything else? Problem 5, homework 16. All right, let me pull that up. Let's see, 223, winter, homework 16. Problem 5. All right, so we have a balanced three-phase system. The source is ABC phase sequence and is delta. There are two parallel Y loads. All right, so we do have a line impedance. We want the delta currents in the source. All right, so I'm going to start drawing a picture then. That's not what I wanted. This is what I wanted. Okay. So let me just jump down here to page 2. All right. So we have a delta connected source. So let's start here and say that this is VAB. This is VBC. This guy is VCA. Here's our terminal A, B, and C for our source. So I've got our delta connected source taken care of. I know that I have a transmission line impedance that's given to me, so I'm just going to call that ZY, put it there. I've got one for this portion as well. And I've got one for this guy also. Here is my terminal B and terminal C for my load. I have two parallel connected Y loads, right? Oh, shit, that one will go there. Here is my neutral. Let's call this guy Y1. And this other guy ZY2. So there's a picture of what's going on. Now let's circle back around and see what numbers we're given. Impedance of load 1 is 4 plus J4. So ZY1, oh, you jerk. 4 plus J4 ohms. Let me save this. And then close this guy out because it's going to keep giving me that error and it's going to drive me nuts. So we were looking at homework 16. Is that correct? 16? And file we had open? Yeah. ZY2 was 10 plus J4. ZW was given as, actually, if you have this in front of you, so I don't have to switch back and forth, will you tell me like what the numbers are? All righty, and then what voltage or whatever are we given? AN1 or AN2? And what was that? I'm sorry. What number? RMS. Okay. All right. Looking for the delta currents. All right, so let's label those guys real quick. So delta currents would be this guy right here, IAB, and this guy here, IBC, and this guy here, ICA. In order to get those delta currents, we are going to need our line currents, IAA, IBB, and ICC. And to get those line currents, we are going to have to determine our phase currents through our load. And I'm putting this as IAN without a subscript because it's going to be the total phase current. BN and ICN. So we're effectively working our way from the load side back to get our source quantities. All right, so based on the information that we have, how do you think we're going to be able to figure out what our total phase currents at the load are? So they will combine into a single equivalent impedance. Sure, but we only know the current through this branch. Find the voltage drop. Absolutely right. So there's a common voltage. I'm only going to do it for one phase. I'm going to call this guy VAN, like so, that we can get to determine the current through ZY2 for the A phase, and then that gives us the total current, the total phase current, which is equal to the line current, and then we can use our the fact that it's a balanced system to figure out what those delta currents are. So VAN is just going to be IAN times ZY1, 56.57 angle 65 volts RMS. So IAN is, oh sorry, this should be IAN 1 times ZY1 is going to be IAN1 plus VAN divided by ZY2. 14.97 angle, what was that? 27.94 degrees amps RMS. We know that IAA, our line current, is exactly equal to our total phase current because we have a Y connected system. So the line current is equal to phase current for the loads because it's Y. And now we're going to do Kirchhoff's current law here at this node. So we see that we have ICA entering will be equal to IAB leaving plus IAA leaving. And we know, so we can move these guys around a little bit. So this tells us that IAA is equal to ICA minus IAB based on the directions that I've assumed for my currents where they're flowing into the positive polarity terminals. I just want to be clear about that. So this is one angle negative 240 degrees. IAB minus one angle 0 degrees. IAB is IAB times one angle negative 240 minus one angle 0. And so therefore our delta current IAB is IAA divided by this guy, which is square root of 3 angle positive 30, I think. I don't know, where's my calculator? Positive 150, okay. One angle minus 240 minus 1. Yeah. And since we know what our line current is, that's a trivial operation. And then you shift it by negative 120 and then by negative 240, and you're good to go. Any questions, comments, concerns about that? Does that approach seem logical?
Well, what I ended up doing, I found the wrong current.
Okay.
I found the delta current through the road.
But there are no delta currents in the load because it's not delta connected.
I don't know how I ended up finding what I found.
Yeah. I mean,
It was would I lowercase a equal to I capital A capital N over 3. I mean, square root 3.
So
Or like, how would that work? That kind of just
so if it were a single delta connected load, IAN does not exist because there's no neutral conductor.
whenever you said these are just the same, that kind of confused me. You know, it's capital A and A. It looks like a delta connecting to A, or it just confused me in the letters.
So these transmission lines, I guess I can understand why. Well, they're neither delta connected nor Y connected. They're just in series between the source and the
I
load.
was thinking both.
Yeah.
Messing me up with the letter.
So I'm saying that my line current is exactly equal to my phase current because my load is in series with my line impedance. But if it was a delta connected load, then my line current IAA would split up by a factor of square root of 3 angle negative 30 degrees flowing into the A phase of that delta connected load.
So then you're going by line.
Right. Let me hold on. 223, winter 21, homework 15, problem 3, you said, right? All right, so we have a YY system, but I want the source voltage. Oh, and you're given the source voltage VAB. So that is the line to line voltage, not the line to neutral volt, not the phase voltage. Yeah. So the subscript tells you that it is the line voltage because it's between AB, not there. So you would have to divide that by root 3 angle 30 degrees to get VAN, and then you can easily have your single phase equivalent circuit with which you can figure out whatever the heck it is you're supposed to be trying to find. The load impedance per phase, all right? And you know the line current. So you know the line current, you know the impedance, you know the voltage drop, so you can do KVL to figure out what the remaining voltage drop is. Divide that by the line current, and that gives you that last impedance that you don't know. If that makes sense. I can definitely write stuff down if you would like me to write things down, or if that explanation was good, we can go with that. Yeah. Okay. Yeah. Yep. So if I have a Y connected source, I can still specify it by effectively using the delta voltages, which seems hinky, but it's just because it's measured between those transmission line terminals. Yes.
So this is an exam question. We will be available to a sheet of paper.
Oh yeah, sure. Sorry. Yeah, you can have an equation sheet. Like I said, the bonus question is only going to be, that's the only what you call it, filter problem that's going to be on that exam. I believe, I mean, we did an example, is going to be fairly straightforward. You can, your equation for that part or whatever, if you want to write down, is literally just H of omega is V out over V in. So I would spend the overwhelming majority of your page, which I'll let you do one standard sheet of 8.5 by 11 paper, front and back, of just 3 phase relationships. And so that would be, I personally, I would write down the different transformations and the rules for all that kind of good stuff. And then maybe the power relationships and the steps for doing power factor correction, something like that. You're welcome to write down more, put down example problems, all that kind of good stuff to help you out. But bare minimum, I would put down the relationships for converting from Y to delta, delta to Y for both the source and the load. Make sure you fundamentally understand, you know, what the difference between a line current is, and if line currents and phase currents, line voltages and phase voltages, all that jazz, because I'm not going to say, I want this. I'm going to say, give me the phase voltage, give me the line currents, blah, blah, blah.
Look past homework 16.
Okay.
So I've looked at power correction stuff, but I'm wondering, like problem 5, this 16, problem 5, 15, if it was like a Y, or it was 3, or 2 loads, it was Y and it does for a Y and Y.
Yep.
Is that like those we're gonna have to do when it comes to that, or is there a chance that we will see like more than 2 loads?
So there might be a power question where I give you 3 loads. So if you look at homework 17, I think there's a problem with 3 loads or something like that. But I wouldn't say like one's Y and it has this, and one's delta and it has that, and the other one's Y or delta. It would literally be specified this much apparent power, reactive power, average power at a particular power factor, blah, blah, blah. Because it's just too much damn math to do it the other way.
So the most that we would be wanting to like get down is just analyzing two loads.
Right. Well, so for a circuit analysis style problem, one load maximum actually. So the homework, the first few problems in the homework sets on three-phase circuit analysis would be more representative of what you should expect on the exam than the last couple of questions where I start throwing curveballs at you by putting multiple loads in and asking for weird things on the other side of the circuit. That's mainly trying to reinforce the whole, this is a balanced three-phase system. You know so much information because it's a balanced three-phase system. Yes.
So, it's like on actual large scale power delivery basis, how do you make those balance? Like your supply power.
Sure. So the company that I work for outside here, Sabre Industries, we make battery energy storage containers that are taking effectively solar systems which create DC currents and all that kind of DC voltages and DC currents, feed them through an inverter, and then they get applied to the grid for large scale grids like in what's powering California and all that jazz. And so we might have loads on those systems like an HVAC unit that's a single phase load. And so what we will do is we'll rotate the effectively how we connect it for every building. So for the first building, it'll be between the A and B terminals of the feed. And the second building, it'll be between the B and C. And the third building, it'll be between the C and the A, so that for every 3 buildings, it's completely balanced. There might be a little bit of unbalanced if it's a number of buildings that isn't divisible by 3, but overall, it's fairly close to balanced, right? It'd be wildly different if we just said, screw it, everything's on the AB, between the A and B terminals, because then you'd have a huge load there and no load between B and C or C and A. So it's just simple little practices like that that are kind of common sense. You just specify building 2 is supposed to be hooked up between these guys, and building 3 is supposed to be hooked up between these other terminals, so that you just rotate it around the phases to balance things as best you can. Yeah. Yeah. Pardon? Well, so I mean, it all depends on what kind of loads and stuff like that you have. So like, I mean, most of the work that I do is with, it's going to be lighting systems and then HVAC systems, which might be 3-phase or might be 1-phase or some combination thereof. So like the compressor might be a 3-phase motor, but the blower fan or something like that might be a single phase, and you can actually go inside of it and rewire which phases it's connected to. It's got a transformer inside the HVAC unit that's easily accessible so that you can do things like that. The lighting loads and all that kind of stuff are all purely real. So you just, generally speaking, try to make sure that you have as much lighting on one phase as the other. It's literally just, let's try to make things as equal as possible. There's always going to be some little amount of imbalance, but as long as it's not too bad, things are generally okay. So did that remotely answer your question? So on the distribution side, I honestly don't really know, because I've never worked in that area. I've always worked on the consumer side of power there. Dr. Batari or Dr. Cox might be better suited to answer your questions, because they do research for the electrical distribution companies and stuff like that. Everything that I do is based on, we're adding stuff to the grid, not the grid itself. So we just, on my side, we just try to make it as close to balance as possible so that the utility companies don't yell at us. That's my goal, is to not get a phone call from the director of AEP saying, you asshole, why did you do this? Now we have to fix something else. Yes.
You don't have to go through the entire problem, but can you for problem 5, just right here would be fine. Can you write out the whole circuit, which the labels one, like IA and IA, or VAB, VAN, because I sometimes get mixed up where I'm supposed to have the directions of the current scale.
So I always have the currents flowing into the positive polarity terminals so that generally speaking, I'm always dealing with absorbed power. That's just the convention that I have adopted. So if I wanted to draw this guy, keep forgetting that I'm on the same thing there. I had a Y connected source, right?
Right. Y connected source and Y delta. Mainly, I understand that both the source side, the load side, I'm confused where the delta and the Y like match together. I'm not sure which ones are A, B, which ones are A.
So the Y's are the ones with the neutral,
Right.
and the deltas are the ones with,
The direction.
yeah. So the current is always going to go from A to B, from B to C, from C to A, or A to N, B to N, C to N. But I'll happily draw it. A, B, C. So, and because this is a Y in parallel with a delta, it's going to be a smidge wonky. So between the A and the B terminals, I know that I should have a delta connected load. Between the B and the C, I should have a delta connected. And then way out here, so I give myself space, I have my delta portion from C to A. And so I'm going to have phase currents flowing this way, and this way, where it's just subscript of the tail, so A to subscript of the arrow B. So A, B, and there would also be an associated phase voltage VAB over that portion, and I could continue on that for all the others, but I'm lazy, so I'm not going to. For my Y connected load, so here's my B terminal, so I'm just going to put my neutral here in the middle somewhere. Then I need to connect from my A terminal to my neutral. And from my C terminal to my neutral. And so my phase currents here are going to be from A to N, from B to N, and from C to N. Yeah. So for the Y connected load, the neutral needs to be the point where all of the loads interconnect, because that's what it means to be a Y connected load. Is you have that one point of interconnection considered to be the neutral. And then there would also be a phase voltage VAN, VBN, VCN, where the positive polarity terminal is on the transmission line terminal and the negative polarity terminal is on the neutral. So like,
Yeah,
just in case somebody else doesn't get it and they're not speaking up, it would be like that. Or that, and then there's also going to be one for B phase of the B phase of the Y connected load. Yes. Yeah, in my opinion, the bookkeeping is the hardest part of three-phase circuits. Once you fundamentally understand what the difference is between phase quantity and line quantity, then it's just keeping up with all these damn subscripts. Okay.
Like over,
Sure, absolutely. I was actually kind of surprised nobody's asked me a power question yet. I'm happy to answer.
Yeah, that's why I didn't even see it.
All right.
Um,
Let me pull up 17 real quick. All right, so just looking at this first one right here, you have a balanced three-phase source and a balanced three-phase load. You're not told if the source or the load is Y or delta. I mean, not necessary to really know. You're given the line voltage at the loads, and you want the magnitude of the line currents and the power factor at which the source is supplying power. So if you know how I would approach problem one here, I have enough information to figure out what the complex power absorbed by load one is, and I have enough information to figure out what the complex power absorbed by load two is. It doesn't matter whether the loads are Y connected or delta connected, they have to be connected in parallel. There's literally no other way you could do it. So that means that the same voltage drop is occurring over both of them, which is this 208 volts in magnitude. So if you know the apparent power, which you can get from the complex power, that will allow you to calculate the magnitude of the line currents. Calculating the power factor will be exactly like we did in the example problem in class. We don't have a line voltage or anything like that. Actually, it's even easier because we don't have a transmission line impedances or anything like that to deal with. So the total complex power absorbed by these two guys must be the total complex power supplied by the source. So cosine of the phase angle gives you your power factor. Easy peasy. For problem two, we have a balanced three-phase source is powering 4 loads. The line voltage at the loads is a particular value at a certain frequency. Now we do have a line impedance we have to care about. We're looking for the magnitude of the line voltages at the source and the power factor at which the source is supplying power. So now we're going to have to pay attention to our transmission line impedance. So here's one thing that's going to be potentially tricky about this guy. We're given the line voltages at the load is 600 volts with no phase angle, so all we know is the magnitude. We're effectively going to have to assume a phase angle for one of them, and then everything else is going to be based off. The reason why I say that is if we want the, well, maybe not. I'm spitballing things here. We have enough information to get the total complex power of the composite load. We can use that to get our line current. We can use the magnitude of our line current to get the losses in the transmission line, which tells us the total power that the source is supplying, which gives us our power factor. And I guess if we have the total power that's being supplied by the source and the magnitude of the current leaving the source, then we can get the magnitude of the voltages at the source as well. If that makes sense. Do we need to work this one to see what the hell I'm talking about here? Yay or nay? You want to work it or not? Sure. Okay. So I'm not going to draw any pictures or anything. I'm going to work it actually. I think there's enough room to work it literally right here. So somebody tell me what the complex power absorbed by load one is. You're given apparent power and a power factor. $29 0.36.
36.26.
I'm sorry, I'm having difficulty hearing. I don't know. I'm old. Here, let me get my calculator. 20 over 0.8. 25. Okay, that's probably what you're saying the whole time. I'm just half deaf. Oh, you're absolutely right. It is kVA, so we have apparent power. We don't need to fix anything. Okay, I made a silly mistake. Okay, so 20, 30, 5.87 or 36.87 with a power factor of 80%. 36.87. kVA. All right. S2 is going to be 10 with an angle of negative 45.57 because it's leading, right? Don't forget about that. S3 is going to be 10 angle 0 degrees kVA because its power factor is 1. So all of the average power is the apparent power. And then finally here for S4, we're going to have 10 over 0.6. With an angle of close 13 degrees kVA. Add all these guys together and tell me what's what. .77 with an angle of what's that? 22.52 degrees kVA. All right. So our line current, the magnitude of our line current is just going to be, sorry, this is going to start driving me nuts. Let me save this and then close this guy down. Discard all that stuff. Look at 17. All right, so 46.77 kVA divided by 600 volts is going to give us what? All right, so 77.78. Yeah. Yeah, only care about the magnitude here. And because I'm dividing kilovolt amps by volt, by a volt or whatever, you're getting a millikiloamp, which is an amp. So, all right. So 77.78 amps RMS. So complex losses in my transmission line is going to be 3 because there are 3 wires times the magnitude of my line current squared times the impedance of my transmission line itself. 0.02 plus J 0.04. So that is in volt amps. So we need to add that to the complex power absorbed by the composite load. Pay attention because the wire one is in volt amps and the other one is in kilovolt amps. So the complex power absorbed by the source is SW plus S1 plus S2 plus S3 plus S4, which is going to give you some number. Tell me what it is whenever you got it. All right, so now we're finally at a place where we can get the answer to part A and B. We've done all of the background work, and now our actual calculations to get the answer is going to be pretty trivial. The magnitude of the line voltage is just going to be 47.4 kilovolt amperes divided by the magnitude of our line current of 77.78 amps. So VL at our source is just the magnitude of SS divided by IL, right? Our power factor is just going to be cosine 23.17 degrees. Actually, I take that back. We're dealing with line quantities, right? So let me, our current might have been wrong originally too. What I'm forgetting about is that this is a three-phase system, not a single-phase system. So I have to be paying attention to things like that. So if you recall, the complex power absorbed by a three-phase system was 3 VP IP angle theta S or root 3 VL IL, same angle theta S. So that means there should have been a factor of square root of 3 taken into account here, and then that same factor of square root of 3 taken into account in our last step. Best guess is they were going to cancel each other out, but we technically did forget to do that. So that is going to influence the complex power absorbed by our wire, though, because we were using a current that was square root of 3 times 2 small. But anyway, so little dumb mistake made in there because I forgot about that factor square root of 3, but the process is fairly straightforward. So I apologize for making that dumb mistake, but we caught it. So problem 3, I think, is an interesting guy right here. It's a little something that you haven't done before. So now one of the loads is unknown, but we have all the other information, so we have to back calculate based on those kind of things to determine, let's see, the average power absorbed by the load and the power factor at which the load absorbed power. So we have our line voltage. We don't appear to have any transmission line impedances that we need to concern ourselves with. We know that the apparent power absorbed by the composite load has a particular value, and the power factor at which the source supplies power is something. So literally find the complex power absorbed, or excuse me, supplied by the source, subtract from it the complex power absorbed by loads 1 and loads 2, which should give you the complex power absorbed by load 3. And from that, you can find the average power and the power factor pretty trivially. All right. Problem 4, three-phase Y-connected source supplies power to a Y-connected load that consumes 50 kW per phase at a power factor of 0.8 lagging. So 50, so total 150 kilowatts. So 50 per phase times 3 phases, 150 kW. 3 capacitors are found that have an impedance of minus J2. Determine the power factor of the combined load. So we know the voltage and we know we have enough information. So we know the voltage over a single phase, and we have enough information to find the complex power absorbed by the load over a single phase, which should give us enough information to determine the impedance per phase, which will be in parallel with that minus J2 ohm capacitor. We combine those impedances together and then recalculate the new power factor. That's fairly straightforward. We're told to do it if the bank is in a Y configuration and a delta configuration. Here, to me, doing it in Y is probably the easiest because we already have a Y connected source and I believe a Y connected load. And then from that, calculate the delta connected capacitance is just let's see. The Y should be 3 times larger than the delta. Yeah, so dividing it by 3. That one's easy. Number 5, balanced 3-phase source is used to supply a balanced 3-phase load, which draws 20 megavolt amperes at a power factor of 0.8 lagging. The line voltages are 4.6 kV at 60 hertz. Determine the size of the capacitors needed to correct the power factor to 95%. Lagging if the bank is connected in Y and delta. So that one's a more conventional power factor correction problem. Calculate S old, then calculate S new, take the difference, divide by 3 if you were doing it on a 3-phase basis, solve for C. Fairly straightforward. So, any other questions with regards to homework 17 or 16 or 15 or anything else? All right, well, if nobody's going to ask me any further questions, then we have wrapped up our review session, and I'll see you guys at 11 on Friday.